This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
So welcome everyone to Software Engineering Radio. My name's Kim Carter. I'll be your host for today. And today we've got Péter Budai. Péter Budai is a computer scientist, a cryptography engineer and vice president of product development at the end-to-end encrypted cloud service Trezor. Péter has an MSc in computer engineering from the Budapest University of Technology and Science. As PhD candidate, he's researched cloud engineering and performance. Péter started his career at Trezor, where prior to his current position, he has led all cryptography-related development efforts as head of cryptography engineering. Welcome to the show, Péter.
Thanks, Kim. Thanks for having me.
So a bit of a disclaimer, I also use Trezor, and I find it excellent as file storage, as encrypted file storage. I've used a few other products like Dropbox and SpiderOak, and found SpiderOak to be a little bit inferior, so decided to move over to Trezor, and it's been really good.
I'm glad to hear that.
So we've had a few shows on a few topics that are related to today's topic. So we've had a show on cloud security with Scott Piper and myself. That was show number 314, where we discussed communications between apps and the cloud and how they're often not encrypted. We had a show on network security with Haroon Mir. That was show number 302. We had a show on application security with Zane Lakey. That was show number 309. And we had a show on Docker security with Diego Monica. That was show number 290, where we touched on Intel Software Guard extensions, SGX, which we'll discuss a little bit later on. So there's a relevant article from the IEEE Computer Society on today's topic. It's called Application Layer Encryption for Cloud. Today we're going to be discussing end-to-end encryption. So we're just going to start off now with some basic questions. What is end-to-end encryption?
Actually, end-to-end encryption means that data is protected from the user's device when it's originating from, all the way to the cloud service provider and back to the user's device. So there's no point in time when the data is accessible to the network provider, to the cloud service provider, or anyone else while it's being transmitted or stored in the cloud or stored in any place in the internet, all the way to the destination. So if we get a traditional example, for example, like messaging, it's a trivial example. So when I send a message from my mobile phone, and when it reaches my wife, for example, the message is encrypted and no one is able to see what's inside, what I was telling to my wife.
Yeah. So it's basically the conversion of plain text to ciphertext, and then ciphertext end to end, right?
Yes, actually, it usually means that the encryption happens on the device, on the user's device, and not on the service provider side.
Why do we need end-to-end encryption? What's the goal here?
The goal is to retain privacy, so we can be sure that no one is able to see our private information, our data, not even service providers, not even internet providers or any malicious parties out there who might be interested in, not even like nation states or governmental agencies. These are a hot topic nowadays. So basically, yeah, that's the point.
Yes, I'm just thinking, like one example would be a European organisation which stores its archive data off-site in the USA, and then under the terms of the US Patriot Act, the American authorities can demand access to all the data physically stored within their boundaries.
Yeah, in that case, if the European service provider uses end-to-end encryption or gives end-to-end encryption to its users, then even if the American part, the American provider, has to give away the data, it'd be an encrypted, like a garbage, which they cannot be really use for anything.
Yeah, so what sort of things are we trying to protect with end-to-end encryption?
Actually, we can protect anything from our personal data, like photographs or confidential documents, to our voice calls, text messaging. Yeah, there is no limit on what we should protect, and actually the more part of our private data we protect, it's the better.
Yeah, also the less suspicious it looks too when we've actually got something really important to communicate.
Yeah, actually, when you when you just encrypt a little bit of your traffic, and someone just eavesdropping your computer, your communication, and seeing that, okay, all the communications were not encrypted so far, but now suddenly it starts to be encrypted. Now it's getting suspicious. So they
Yeah,
are.
exactly.
That's the interesting part they would like to look into. So the more we encrypt, actually, the better we have.
Yeah, so who are we trying to protect it from?
Generally, we would say the any malicious parties like hackers or hackers who are trying to make profit of our private information on the black market. But if we think about B2B scenarios, then we should protect our data from our competitors, for example. So if we have a new patent pending, for example, or a new invention, we would like to keep it secret for our competitors. There are a lot of risk groups, for example, like journalists or non-governmental organizations who are working in rather dangerous areas, and a lot of times their life are depending on whether their whereabout is not public, so
Yeah,
they
that's
can
true.
keep it secret.
Yeah, I know someone that actually works with children that have been abducted, and yeah, that's really important for her as well. So what are your thoughts around adding backdoors for the authorities, but somehow stopping the attackers from using them?
Generally, I don't really have good opinion on backdoors. I don't think backdoors are a good way to achieve what they are trying to achieve. Usually backdoors are originating from two sources. One are just simply mistakes, programmer mistakes, or bugs in the code, which can be then later exploited by hackers, for example. And the other source of backdoors, when someone just plants an intentional backdoor in the application to later gain access to the information. The traditional, so we can say that traditionally these are planted by governmental organizations. We could read in the news about the lot of NSA scandals, like the most famous one is the one from with Edward Snowden involved. And yeah, they are putting backdoors to in the applications and cryptographic elements and cryptographic standards to later have control over the data and be able to decrypt the encrypted information. My opinion is that these backdoors cannot remain like secret forever. Not even agencies like that or companies can keep secrets forever. They are not invulnerable to similar attacks as well. So when these backdoors are getting public, so it's known by everyone, suddenly any malicious person will be able to use this backdoor to get access to the information. And usually at this time the affected software and the affected hardware component is already widely deployed in the world. So there it will be really hard to find the mitigation against the backdoors.
For our listeners, can you explain symmetric and asymmetric encryption?
Yes, of course. Symmetric encryption is like the easiest one to understand. It gets its name because the encryption and the decryption uses the same secret. We like to call it a key, similarly to a padlock with a key. So when you encrypt the data, you get your plain text message, for example, an email, and use it a key and use cleverly designed algorithms that clever mathematicians all over the world created. And with the key, you can encrypt the message to another document which looks like complete garbage to the one who does not have a key. And then you can send this encrypted message over any kind of transport channel, and then at the other end of the channel, if someone knows the key, the exact same key, then he or she will be able to decrypt and see the email message that you just encrypted. So this is the symmetric encryption. The asymmetric one is a bit trickier. It involves two keys actually. So if I would like to send a message to you, I would need your public key. I have to know your public key, which then I can use to send and to encrypt a message and send it to you, and only you will be able to decrypt it. But anyone in the world can create a message and encrypt it for you. Only you will be able to decrypt it, and you will use your so-called private key for decryption. And the point of asymmetric encryption is that your private key is secret. You keep it to yourself. You never tell it to anyone. But from your private key, you can easily calculate the public key. And the public key has the name public because it can't be distributed anywhere or in any way. For example, you can just create a newspaper advertisement containing your public key, and then anyone can see and use your public key to encrypt messages for you. The point that from the public key it is like impossible to calculate the private key, but from the other way around it is feasible easily. So the advantage of using asymmetric encryption over symmetric encryption is that I don't have to meet you. I don't have to know a shared secret to send a message to you. On the other hand, when we would use symmetric encryption for communication, then we somehow need to exchange the key, need to agree on the common symmetric key that we use to encrypt and decrypt the messages. So this is the biggest disadvantage of symmetric encryption, that the key needs to be somehow shared, and I just cannot send the key via a normal communication channel, because that would be equivalent of sending the message. Because if I send the key in plain text, everyone is able to see the key, and then they can use it to decrypt the message. So with asymmetric encryption, this is not a problem. However, there is a pitfall. Usually, asymmetric encryptions are much slower than the symmetric ones. So there is always a trade-off whether which encryption to use. In software engineering, we use symmetric encryption everywhere where is possible, and using asymmetric encryptions only on that parts where it really matters to have public keys, or we need key exchange. Usually asymmetric encryption must be used only for key agreement and key exchange for symmetric encryption, and no real world application uses asymmetric encryption for actual data or message encryption.
So what are some of the different types of symmetric and asymmetric encryption?
Usually there are a lot of algorithms. During the history of cryptography, they were inventing a lot of algorithms. We can talk about stream ciphers and block ciphers.
Maybe just some of the more commonly used ones.
All right. The most commonly used nowadays is AES, which is asymmetric encryption, and on the asymmetric part there is RSA, which is the most well-known one, and the different elliptic curve algorithms are also getting popular because they are generally faster than RSA and they have smaller key sizes. So yeah, triple DES or triple DES, AES, RC4. These are the symmetric algorithms, can quickly tell, and RSA and yeah, curve 25519 is an asymmetric, for example, or DSA. So there are several others.
Have you got some examples where these are used, where the different algorithms are used?
I'm aware that most of the disk encryption tools that's either built in the operating systems or can be used differently. For example, the Microsoft BitLocker or the Lux encryption in Linux or the Veracrypt application. So they are using AES encryption for disk encryption. The secure web itself, it's using most of the time it is using AES with 124-bit keys, for example, and the same secure web. So the HTTPS is also using RSA and Diffie-Hellman key agreement for key exchange. So, for example, in secure web communications, both type of encryption is used. Yes.
Yeah.
Actually, the SSH secure shell is also using both encryptions. They usually both HTTPS and SSH is they are supporting different set of algorithms, and the server and the client can agree on the beginning which ones to use, and they usually support all that I mentioned.
What types of systems can we apply end-to-end encryption to?
Usually, the trivial answer would be where there are two ends to the communication, but there are a lot of examples. We can use end-to-end encryption like text messaging, voice calls, video calls, file storage, for example, and these are mainly the main ones I'm aware of.
What types of systems should we apply end-to-end encryption to?
That's an easy one. All. Yeah. Actually, we believe that the most systems use end-to-end encryption is the best for privacy and keeping people's privacy the way it is private.
So we're going to discuss instant messaging, voice and email scenarios briefly, and then move into inter-service communication scenarios. So in the instant messaging scenario, we apply end-to-end encryption to instant messaging. Some of these offerings are Signal, Wire, Facebook Messenger, if you opt into it, WhatsApp, Telegram, Viber, iMessage. What are your thoughts around these offerings and their ethics?
I'm pretty glad that we have a lot of text messaging services, and I also like that the most of these services are built on the same protocol, which was developed by OpenWhisper Systems. It is the Signal protocol, and it's a pretty well designed protocol to use it. And yeah, actually, the differences originating from between these providers that they are making decisions whether making the encryption, the end-to-end encryption, a default one or just an opt-in feature, whether how directly they are communicating the cryptographic operations that's happening in behind. And these factors can be affecting how people are using these services, how easy they are to use, and the level of security as well. So regardless of using the same protocol and the same messaging implementation under the hood, there are also some differences and which affects the security.
Yeah, I'm just thinking, I like with Signal, so like the actual algorithm is free and open source, and they retain your phone number and last login date, but nothing else. There's no other metadata that they retain. And the likes of Wire is open source. Its headquarters are in Switzerland, and it's got EU servers, which I think is quite a big plus because the governmental restrictions around who can access your data and that sort of thing in Switzerland are very strict. And they use the Proteus algorithm, I think, which was an implementation of the XOLOTI protocol. I forget exactly how you say it, but it was later renamed to the double ratchet algorithm, which is, I guess, what Signal's based on. And then you've got like a Facebook's Messenger, which is, of course, opt-in and uses the Signal protocol, but it collects a lot of metadata from users. And then you've, like with your WhatsApp, again, it uses the Signal protocol, but collects a conversation and a lot of other metadata. And it's owned by Facebook, and the user's data goes to Facebook. So there's things like that. There's actually quite a bit to weigh up there, right?
Yes, actually, that's the toughest part of it from the user's perspective. I think that even if we would like to keep our privacy, and we are trying to keep to have an open eye on secure solutions and try to use the most secure one. Actually, in these days, the user has to be really careful and aware of what services they are using and how actually they are working, what information, what metadata these services are collecting. So this is a hard question. On the open source topic, I think it's really great to have these underlying protocols as an open source, because then it gives even developers or security researchers an opportunity to review and see whether actually what's implemented in the library, in the protocol, is implemented well, because it's really easy to use cryptography in a wrong way. So it turns out that it does not protect at all. But yeah, even if someone builds on the same library, on the same protocol, it's still you can make wrong decisions and use it wrongly.
Yeah, I'm just thinking about the likes of Facebook, WhatsApp, Telegram, and Viber. They're basically using encryption as a marketing thing, basically to pull people to use their application, but they're still collecting loads of metadata on their users and passing it on to other entities and that sort of thing as well. So the likes of Telegram, there's been controversies around their hand-rolled MT protocol, and again they store lots of metadata. Viber has got a hand-rolled closed source Signal protocol. And then there's iMessage, which is the iOS offering, which is end-to-end encrypted. But it's closed source, so I guess it comes down to whether you want to, whether you can trust iOS. I mean, there's possibly a backdoor in there.
Mm-hmm. Yeah, actually, if you're using closed source solutions, then you have to have trust in the service provider, and at some point you have to trust in something. But the more thing you see, the more thing you are able to check and look through, then the less thing you have to worry about. But for example, that's I find it interesting that if you are using end-to-end encryption, I'm just reflecting to our first topic now. It means that if you use end-to-end encryption, for example, then you don't have to trust the cloud or the service provider because it doesn't matter whether they are saying that they won't touch your data on they store it encrypted or they use secure transport channels, because from the point that you start using end-to-end encryption, it doesn't matter anymore, because the messages are protected either way, from when they are originating to all the way to the target. So that's an interesting topic, that you have to trust the encryption and the end-to-end encrypted service itself, but you don't have to trust the network provider, and don't have to trust the service provider or the cloud provider. So that's an interesting topic.
Yeah, the other issue is like the metadata, right?
Yeah, the metadata is always a difficult question. Usually they are documented, or at least they should be documented in the terms of use section, or in the privacy policy. Actually, the now that GDPR is coming in the EU, there are a lot of restrictions, and there are more things these companies have to document, where our data and metadata are going, what are they doing with it. So it's getting more visible from now, and I find it a good thing as well.
Yeah. So with the voice scenario, we've got offerings again. Signal, which is a voice and video over IP. Silent Circle has an offering called Silent Phone. We've got FaceTime, which is an iOS offering. WhatsApp again, and Skype, which is pretty much known to be spyware. What are your thoughts around these offerings and their ethics?
Actually, I'm not really familiar with them. I'm not really using it. I think using end-to-end encryption in voice calls, it's not much different than using it for messaging, for example. So the principles are the same. The only difference is that there are more data to encrypt, and they have to be more performance optimized. So because video and audio has a lot more data to encrypt and send through the network. So yeah, my opinion, if we trust, for example, iMessage, then why wouldn't we trust FaceTime? It's the same provider. I don't see much difference in if it just depends on what kind of data we are encrypting. Can I reflect on the hand-rolled encryption part you were mentioning with Telegram?
Yeah. Yep.
I was reading through the articles about Telegram, and I would like to mention that hand-rolled encryption has like levels. On which level you are using hand-rolled encryption, and actually there are the level of cryptographic primitives, the AES block cipher encryption, or the RSA standard, or hash functions, or these really low level operations. And the rule of thumb is always that you don't implement your own cryptography. And for example, in case of Telegram, they are using well-known primitives, so they don't use hand-rolled encryption. And the next level is how you put these together to create a service or create a protocol, for example. And you can make mistakes here and at any point. And again, if you have some well-known protocol to use, then you should use that. You should stick with that, because they have proof. They are proven that they are okay. For example, if you would like to authenticate users with password, you are using the SRP protocol, which is designed for that. But not to mention that this protocol has now the 6th version, because the first 5 was not so perfect. So even the standardized protocols have flaws. yeah, but if you are dealing with a field where there is no proven protocol, then you can, and it's not, if you do it right, it's I don't think it's they are much vulnerable if they are doing it right. So putting cryptographic primitives together to form a protocol or create an application, if done well, it's can be told that it's hand rolled, but it's hand rolled on a different level. So it's not on the cryptographic levels which are well known. We at Trezorit, we also have parts in our protocols that would be called hand rolled in this term, but we don't count it as hand rolled cryptography. We also use standard algorithms. We use standard protocols where we can.
Yeah, so it's more about the native algorithms, isn't it? The other low-level ones. So moving into the email scenario. Email is not end-to-end encrypted unless we're using GPG or PGP, which is a pain. TLS provides encryption to the server. Start TLS can provide encryption between the servers. Google made various announcements from late 2013 through to about March 2014. They now provide not only mandatory TLS encryption between clients and their servers, but also between their own data centers. Now, this is good, but it's not necessarily end-to-end encryption. So there's transitional seams between each server, when the data goes from resting to in transit and vice versa. The NSA and GCHQ are more than likely have backdoors into their servers as well. So I think it's safe to say if we want email or any cloud privacy for that matter, we need to take the responsibility ourselves. Is there any hope here? How can we improve the email situation?
Yeah, actually, the problem arises from the fact that email was created way before then, when the encryption was a necessity back in the days of the internet rising. So there are a lot of solutions already. It's not just PGP, but there is SMIME, which is not well known, but it's also a standard protocol. It's implemented a lot of mail client applications as well, which is also using asymmetric encryption and certificates like PGP do. So it is similar to that. And during in the times in the last 10 or 20 years, computer engineers try to make email secure, but having a TLS channel, a secure channel, when we are transmitting email, so when I transmit my email to my email provider, to my SMTP server, then they are transferring it all over the network. You have to know that your email is like hopping around tens of servers before it reaches the final destination. And nothing enforces it to have all the hops, all the steps being encrypted between all the servers. So there can be any part of the transmit where your email will be transmitted without encryption. And that's the flow of the protocol. And I really appreciate Google, who was a pioneer in making Star TLS and TLS in email communication mandatory. It is great, but it doesn't make it end-to-end encryption in the sense that we were talking about in the beginning of our conversation. So being the email encrypted in transit does not mean that it's not accessible to the email servers or the email providers during transit or at these points where it's just switching direction. So the real solution here is PGP or SMIME, but they are really hard to use for an average user. It's true that they are not easy to use, and there are a lot of initiatives to make email secure. There are some secure email providers who try to make it easier, like ProtonMail, for example. If you are communicating between two ProtonMail users via email, then you get encrypted email automatically without any kind of setup or hassle, which is great. The same applies for Tutanota, for example. So there is hope. I'm so there are a lot of providers who try to fill this gap to make email secure without the hassle of setting up PGP keys and all the stuff that makes it complicated for an average user.
Yeah. So we're just going to move into the inter-service communication scenarios now. As software engineers, we're building complex and distributed systems to run on servers we know very little about, aka the cloud.
Mm-hmm.
This is untrusted territory. Why do we need encryption between these components?
Usually, can you be a bit more specific, or do you have some examples I can reflect to? It would be easier to answer.
Yeah. So say you're an organisation, you're developing, basically any sort of a system in the cloud, and you've got a bunch of microservices, and they're all talking to each other. So why do we need end-to-end encryption between those microservices and I guess the end user?
Mm-hmm. Actually, that there is the same principle. To be short, it's the same principle that I was already talking about. So they don't have to trust their own cloud provider. If you don't depend on the cloud platform's encryption, but do it on your own. And if you do it on your own, you can do it in an end-to-end encrypted way, or you will actually end up doing it in end-to-end encrypted way. Then you are not depending on the cloud provider. You don't have to check the news whether they are already being hacked or some flaw is discovered, because the communication between your software components, whether they are being for example, microservices or different microservices or a service and the user application, the user's device, you don't need to configure and monitor and be aware of the cloud provider's encryption solutions. And yeah, it then depends on the level of security you would like to achieve, or the level of encryption, the level of protection, the data you are communicating. So if you are dealing with, let's say, some medical devices that constantly sends medical information, for example, heart rate or blood sugar levels to a cloud service, then it's actually considered personal information, and you have obligations to protect them better. And for in this scenario, you cannot do anything else but use end-to-end encryption, because that's the only way you can achieve that level of security. Then you can be sure that even if in the very, very unlikely scenario whether your cloud provider gets hacked, or there is some malicious employee who at the cloud provider who tries to dump all the information, or just tries to steal a hard disk, they won't have access to any critical information, or any private or personal or healthcare records. So that's how you can, for example, adhere to the law in these terms.
Yeah. So securing data at rest and in transit is generally a solved problem, but securing data in use is harder. If we can achieve this, then we can achieve end-to-end encryption. If we have to decrypt in order to process, then we've got a seam, and this is generally where attackers will focus their efforts. So rather than creating a seam in our end-to-end encryption by decrypting to perform processing, let's look at some techniques for securing data in use. So this is providing end-to-end encryption. So I've got a selection here we're just going to walk through. I've got full memory encryption, CPU-based key storage, enclaves, and cryptographic protocols. So let's start with full memory encryption. So the system provides both confidentiality and integrity protections of code and data, which are encrypted everywhere outside the CPU boundary. Can you explain how this works and how software engineers can take advantage of it?
Yeah, I would like to do a bit disclaimer that I'm not I'm really expert on these. I'm aware of basically what they are doing, but I try to do my best. So I like to start with full memory encryption. It means that usually we, like in the computer engineers think that the level of protection is the boundary of the hardware or the boundary of the computer. So if I have my laptop in front of me, that's the level of protection that we need to focus on. So whether my laptop is stolen or not, but we don't take into consideration when we are designing software or hardware that someone just comes and takes out memory of the memory module of my laptop. But in the cloud, for example, it's a bit different because there is a lot of hardware next to each other, and software are using the same hardware virtualized on the same environment. So there is more need to protect each from other, and from any kind of flows.
I'm just thinking about the Rowhammer attack. I think it was called the Rowhammer attack, where some researchers uncovered that the attackers were able to actually get access to the memory sitting right beside another row.
Yeah, and that's an example, for example. And what full memory encryption does is that also encrypts the memory, the operational memory of the computer, and the encryption is done by the CPU itself, and it happens transparently. So different parts of the memory are encrypted with different keys, and the different keys belong to different software. This is quite a new advance in CPU design. Actually, to be honest, I find it more like a marketing invention or for marketing. Recent events shows that if there is a flaw in the CPU design, it doesn't really matter what protections the CPU is offering, how many layers of encryption you are putting to your memory. If there is a flaw in the CPU design, then the attackers will just focus on that. And if you have a flaw in your CPU, then you will be able to recover the encryption key for the memory. So it doesn't really matter whether you encrypt the memory or not. So it's very limited scenarios where full memory encryption can help. Usually normal protections built in the CPU, like memory virtualization and protection bits, should be enough to protect different programs from each other, or different virtualized operating systems from each other. Full memory encryption is just an additional layer, which I don't think it has much more use. But
right,
yeah, it's my personal opinion.
Yeah. So what do you think about CPU-based key storage? So this is where a kernel patch provides CPU-only based encryption to defend against the likes of cold boot attacks, allowing RAM to be treated as untrusted. Can you tell us a bit about this and whether software engineers could be and should be able to use this in the systems we're constructing?
This actually also, I also find a very limited use of this. This usually used for like bootstrapping problems when you have someone somehow have to provide a secure environment from the beginning. It's like the similar concept to secure boot, for example. So you somehow the operating system has to start and have to get into a state where you can be sure that no one was able to change the code or change the environment before you start the real operation. So yeah, CPU based key storage, because in in the CPU there is really limited space for keys and operations. There is also like a smaller set of data that can be encrypted and decrypted, and usually these are just keys stages where you can just use these keys to decrypt and validate the other parts of the software, which in turn will be loaded into memory. Yeah, in some really security critical parts, or for example when you have to design security modules, for example, or the smart cards or something like that, it can be a useful solution, so you don't have to expose your data to the data bus or to the memory. But again, I find it a limited scope, so it's not a general solution you can apply.
Right. Okay. So let's have a look at enclaves. So we touched on Intel Software Guard Extensions (SGX) in the show on Docker security. That was show number 290. Data in enclaves is encrypted in RAM, but clear text within the CPU and its cache. Intel introduced this concept of enclaves as part of their SGX, providing a set of new SGX-enabled CPU instructions, 18 of them, I think, allowing user-level code to allocate private regions of memory known as enclaves. Mm-hmm. Intel has this concept of symmetrical provisioning key, which resides in both the SGX-enabled chip and on the Intel servers. So to establish an enclave, the software needs to offer its provisioning key to Intel, and if there's a match in their database, Intel will issue an attestation key that lets SGX set up the enclaves. So SGX has been heavily criticised by security researchers. Some of them were MIT, Victor Kostin and Srinivas Devadis. So as far as I can tell, by using SGX, we're just shifting the trust from untrusted clouds to Intel. So we're essentially just shifting where we trust. Would that be your take?
Yeah, exactly. Actually, that's the same debate. For example, again, I can refer to Secure Boot, which also had this controversy when it was initiated by Microsoft back then. That okay, Secure Boot is great, but if they are controlling the keys, then what's the use? But but it's not black and white. I find secure enclaves, SGX an interesting concept, and I find a lot of uses. And I'm working in the cloud industry, and especially in the cloud industry, that's a promising solution to trusted computing problem. But the scenario you were mentioning, that somehow you have to process the data, but in a way that it's not accessible to the service provider, because if you decrypt the data, then it's already exposed. But if somehow you manage to keep it private, then you can create a lot of operations. So now there are major cloud providers, for example Azure, they are rolling out secure computing, which is based on Intel SGX. And while it being a relatively new concept, like it's introduced 4 years ago or 3 years ago, And in the security world and cryptography world, it's not a long time to make it mature. And yeah, actually it has faults, but I think they have a lot of promising concepts. And yeah, in the cloud, it will good that I will be able to deploy an application which operates on private data in a way that I don't have to be cautious whether my data is accessible to the cloud provider. However, it brings up another problem, which is how my code, how the data is getting to the enclave. So so it's always a boost. There is always a bootstrapping problem. It's with end-to-end encryption. Okay, you have end-to-end encryption, but somehow you have to manage the keys. So you have to exchange the keys. So on the other party will be able to decrypt. So that's the problem you engineers have to solve. Intel has an option for that, which is remote attestation, which is again involves registering at Intel, and yeah, there is some controversy around this. Yeah, I hope that they somehow will open up this platform more, and then I think it will be usable.
I think the SGX patents disclose pretty much in no uncertain terms that the a launch enclave was introduced to ensure that each enclave's author has a business relationship with Intel and implements a software licensing system. Mm-hmm. So basically, we're just shifting our trust to Intel.
Yeah, the same happened a few years ago when Intel VTD was introduced. It was the same issue. Yeah, it seems like Intel is like this kind of solutions, whether they have a key or a backdoor like access to our devices. I hope there are a lot of other CPU vendors, so we'll see. I hope for the best.
So just moving on to cryptographic protocols. So I've got secure multi-party computation and homomorphic encryption. So with secure multi-party computation, also known as secure computation or privacy-preserving computation, the idea here is to create methods for parties to jointly compute a function over the inputs while keeping those inputs private. And then with homomorphic encryption, this allows us to perform computations on ciphertext, the result being the result of the operations as though they had been performed on plain text, but still encrypted. Can you explain a bit about secure multi-party computation and homomorphic encryption and how they differ?
Yeah, actually, it works in a way that you described. Again, I'm not a great expert on this, but they are really, really, really interesting and more like in a crypto nerd way interesting. As far as I know, they are still in academic research phase. As I know, they are too slow currently to make it usable in any kind of real world applications. But yeah, they work in a way that you have an encrypted data, and it's encrypted in a special way which allows certain operations to be performed on the encrypted data, and then you get back an encrypted result, which is then, if you decrypt it, you get the actual result of the whether if you perform the operation on the decrypted data, but you don't have to decrypt it. And the promise here is that if you are able to perform operations on encrypted data, then you can offload a lot of computations from the client side to the server side, while you don't have to give up the encryption and don't have to give up the privacy. Yeah, there is an example which is like feasible right now, which is encrypted searching. However, it needs So you are able to, using Bloom filters, for example, you are able to do a search on a data that you don't know, and you don't know the search term actually, which because it is encrypted or not, it's converted in a way that you cannot get the original search term back, and you have a lot of you have a huge index of the information. Then you can perform a limited search, for example, on encrypted data, and you will get which encrypted part contains the data you are looking for. But this is also costly in the terms that you have to maintain a lot of indexes and huge index databases. So there are some researches, but unfortunately they are still in a phase that they are not fast enough to use in production.
So the indexes are indexes of hashes, are they? And they're just comparing hashes with hashes.
Yeah, that's a really basic example. But
Right.
but that's just for looking for an exact match. But searching is a bit different. And you would like to look for substrings, and you have to look, well, you would like to look for like a word in a 100-page document, and you would like to find that. So yeah, hash matching is one special case of encrypted search. But yeah.
Right. So it sounds like it's not ready for prime time yet.
Yes.
So now that we've talked a little bit about securing data in use, what are some of the best options for our software engineers today to perform processing on encrypted data? Or are there any?
Not really. So what you can do is decrypt it, and then do the operation and then encrypt it again, which makes for in the end-to-end encrypted example. So if you are using end-to-end encryption, it makes it really difficult. This is, for example, a problem we are facing, that all operations have to be done on client side. So like these data transformations on migrations or anything like that has to be performed the client side. So we somehow have to wait for or ask the user to log in to and to his device or his client, for example, and it makes it really a challenge to implement changes and protocols, because if you rely on your users to use their clients, they won't they there will be always a lot of users who are not using, they are traveling around the world, or just simply stop using the application, and then you are stuck with a lot of data that is not that you cannot migrate, and you have to support all protocols and all standards for ages. So it's a really difficult part if you choose end-to-end encryption and you don't control both ends of the encryption. If you have controls, for example, if you have like the microservices example, and you have 2 or 3 microservices communications, then of course it's not a problem because you control both parties. But if like real world users are involved, it's getting difficult.
Yeah. So I'm just transitioning now from end-to-end encryption to encryption between points of communication. So we touched on what CSPs are doing to encrypt our comms between data centers and services and components in the cloud security show. That was with Scott Piper, show number 314. So it basically came down to we don't really know what they are doing, so it's up to the developer. We can set up mutual TLS authentication between our components.
Mutual TLS authentication is not, if it adds a layer of security to the communication, because not just a single part of the single party, single peer of the communication is authenticated, but also the other peer. So if you use mutual authentication, you can be sure that really no one intercepts your traffic between your services. Usually combine it with depending on the architecture used. So if for example if you are depending on virtual machines, for example, so combining with disk encryption and secure communication, actually you are creating a closed loop where information cannot really go out. You can also set up, if you have a cloud application, for example, and which is distributed in different data centers around the world, then you can set up secure VPN connections between your data centers, and then you are creating a whole private network of between your computers or between your services, which is also adds security to your application. And yeah, then there are different ways you can communicate via storage. For example, if you use encryption before sending the data to the storage, and the other service is using the storage as an input, then you also created a secure communication channel between your services, for example. Other than that, yeah, suddenly I cannot tell. I'm not aware of other solutions. These are the traditional solutions and
Yeah, right.
the solutions that are used in practice in the cloud nowadays. So secure communication, which is actually usually it's a basic thing to have, and VPN communications, encrypted storage.
So just moving on to libraries, ciphers, and tools. So there's a huge amount of poor advice that I think pretty much most of us are aware that are on the internet, on the likes of Stack Overflow and that sort of thing. Let's get some solid advice for our engineers. What ciphers and modes should we be avoiding, and which should we be using for which purpose?
That's yeah, that's a more complicated question that it seems, because it really depends on what you are using the encryption for. For example, if you are developing an application for government or military, for example, then you will end up with a lot of standards like FEPS or common criteria and things like that that makes a specific cipher and a specific mode mandatory, for example. But that's an extreme example. Generally saying, if we stick with modes, so let's say AES and the different modes of how AES can be used. Generally speaking, ECB, which is electronic codebook mode, is it's really hard to use properly. So if you don't really know what to do, don't use it. That can be a rule of thumb. But that's where it actually ends, because the other modes are usually play well in terms of security, but all of them can be used improperly. For example, if you are planning to develop a disk encryption or block encryption software, you will end up using XDR mode, which is the one of the newest modes and especially designed for disk encryption. CBC or CFB are the general way to go. So these are the traditional modes they are using. But for example, for CBC, there is the padding oracle attack, which should be avoided with message authentication. So there's all the modes has some points where then they can go wrong. GCM, for example, I would suggest GCM because it's not just it's actually easy to use, and it also has message integrity built in, so it will be faster, for example, and also you get message integrity. You don't have to use a message authentication code in addition to encryption to provide integrity. Encryption itself is not is never enough. You have to provide integrity, and GCM does it in one step, for example. So yeah.
Yeah. So it can be hard for software engineers to know which ciphers and KDFs they should use. KDFs being key derivation functions. What do we need to look for in a library?
Yeah, that's an easier question. I would go. I think the most important thing that the library should be maintained. So that's one of the first thing that if we, for example, at Trezor, if we choose a library, a third-party library, we see whether is it actively maintained or not. Having a library that is not touched like for 2 years, and it seems like it's okay, but at the point when you find some bugs or flaws or something turns out, then having a quick fix is can be essential for you. So active maintenance is a key point. Of course, if you can find some informations regarding whether is it was it reviewed by a security expert or an organization, does it have any certifications or public reviews, how many other softwares are using it, so they're just good. If you don't have if the library doesn't have any kind of certifications or security audits, then the number of users can be a good heuristic whether is it good or not, but it's not generally applicable. So there may be, for example, OpenSSL 3 or 4 years ago, it was everyone was using OpenSSL, and it turned out that Heartbleed was affecting almost the 90% of the internet. So it's not always the case, but it's a good heuristic. And yeah, for example, if you are developing and closed source or an open source software, you also have to check for the license as well. So yeah, these are the factors.
And what about how important is it that it's actually created by cryptographers?
Yeah, that's always a good sign if some of the editors or contributors are well-known cryptographers. Yes.
So just got a question around a Trezor non-convergent crypto. So Trezor uses non-convergent crypto to store users' data. Can you talk a little bit about this and what it means?
Yeah, I would invert the question. So what does convergent crypto means? It means that if you are encrypting the same data, then you will usually end up with the same ciphertext. So for example, if there are several users who are uploading 1 GB video, there was a birthday party, and everyone is just uploading the video of it, and the same video is uploaded by several people, then it can be used to deduplicate on the server side. So the encrypted content will be the same. If the same file, the exact same file is uploaded, then the encrypted form will be the same, so you don't have to upload it again. Most of the cloud storage providers use it as a form of deduplication, and it's actually not a bad thing. So it's not a thing to avoid in any cost, but it means that, so let's see, there is a warrant, for example, from a government organization. So they would like to know what a user is storing at their storage provider. And the storage provider, in case of convergent cryptography, the storage provider cannot tell what the user is storing. But if the government gives you a file, let's see whether this file is uploaded. Let it be some illegal content, for example. Then the storage provider can tell whether this illegal content is in the user storage, because the same content will be resulting in the same encryption. So it can be used to prove whether a given content is in the possession of a user. In case of non-convergent crypto, this is not the case, because every time a file is uploaded, a new key, a new IV is generated, and then it means that the resulting ciphertext will be different each time. So this kind of claims are not feasible. So we cannot tell if someone gives us a file, or let's see whether this file exists in any of our users. We cannot tell it, because the same file will always result in different results, different encrypted forms.
Yeah, it's these sorts of things that pretty much won me over to actually go with Trezor, along with the likes of Trezor's bug bounty, which I think had something like 1,000 hackers hacking on it. Was that right?
Yes. We offered $5,000, $50,000, sorry, to the ones who may be able to break our encryption, and actually we weakened the encryption. So at Trezor we have at least two levels of security. So there is the end-to-end encryption, and then plus the traditional security layers like secure communication channel, TLS, and server-side authentication, and all the traditional stuff. And the last part we were opened. So only the end-to-end encryption part had to be hacked, and fortunately they were not able to manage to hack it. But to be honest, that we were expecting.
Yeah, it's a pretty good testament. Hey, we're going to have to wrap up. So thanks for joining us today. It's been really educational and fun, Peter.
Yeah, thanks for the opportunity as well.
For Software Engineering Radio, this was Kim Carter.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.